Okay, welcome everyone. Really excited to see still so many of you show up towards the end of 2 days really exciting Spark Summit. So my name is Arthur. I'm a tech lead at DataVisor. Here's my colleague Ting Fang, who's a director of research at DataVisor. So DataVisor is a Series C startup. And our main business is to provide anti-fraud solutions to large enterprises like Pinterest, Yelp, and many more. So today, here, we are really happy and excited to share some of the exciting results by applying deep learning in anti-fraud in production and also in a startup environment. And also, in the meantime, I would like to share with you some of the lessons and experiences learned through building this deep learning in production infrastructure in a startup environment. So with that, I will hand over to my colleague Ting Fang, who will start the presentation.
All right, thank you, Arthur. So before we dive into the details of deep learning, I want to give you just a little bit high-level information on modern online fraud. So traditionally, when people hear fraud, you think of transaction fraud. Somebody has a stolen credit card, they make a purchase that results in the chargeback, and either the merchant or the bank takes the hit. But in reality, online fraud is much more complex and diverse. And this is due to the many different new features that are available on online services that we use every day. And you may even have heard about some of these newer attacks already in the news. Now, these fraud attacks are costing online services millions of dollars in losses per year. But not all of them are exploiting vulnerabilities in the service. If you think about it, writing a review is a perfectly valid action on a social network. Never mind that it's a fake review somebody paid me to write. So these fraudsters are simply abusing the already available features on these platforms for financial gain. And to do this, all they need is just to create user accounts, or even better, just to compromise existing users. And that will give them everything they need to conduct their attacks. Now today, these fraud attacks are largely orchestrated by organized crime rings. They're controlling fake and or compromised accounts en masse. And the underground fraud economy is also very specialized. There's a market of suppliers that provide services for all aspects of the fraud operation. For example, there are people who specialize in registering fake accounts. And there are people who specialize in providing the network infrastructure for carrying out your attacks, including data center or proxy services to hide the attack origin, as well as redirection or other types of obfuscation to hide the malicious content. Existing fraud detection approaches typically rely on blacklists or reputation lists to block known malicious activities. Or some of them also rely on a large set of label data and extensive feature engineering by human analysts to train the model. And as a result, this sometimes produces models or produces results that are very specific to this particular online service or very specific to this data set. And they do not generalize well to a different type of a fraud attack or to changing attack patterns. A more recent approach to online fraud detection is unsupervised machine learning. The idea here is that these bot accounts controlled by organized crime rings behave very differently from normal users. They act in a coordinated fashion. And so by examining groups of correlated users together, we can start to identify patterns that were not previously visible when you view these users in isolation. And of course, the main benefit of unsupervised machine learning is that you're not reliant on examples of known attacks. At DataVisor, we work with some of the largest internet properties across the world, spanning multiple industries, including financial, e-commerce, gaming apps, mobile gaming, and social networks. And we have a production unsupervised fraud detection solution running for the past 4 years or so, generating a large data set of fraudulent accounts on a daily basis. So as we have started to observe more and more fraud attacks, we also started to notice that there is a lot of commonality across our clients' data and across the fraud attacks that they face. There are certain events, or there are certain data fields that are present in almost all application level events, regardless of whether This is a account registration event. This is a payment event. This is a money transfer event. This is a messaging event. This is post. This is review. This is user follow, or even level up events in mobile gaming apps. We started to think that maybe we can leverage all this common information across all of our clients' data to boost our fraud detection capabilities. Now, if we can collect all these common fields across all these application level events, we can have a pretty impressive database of common digital identifiers, including IP addresses, email domains, user agent strings, device types, or phone number prefixes. In addition to just these identifiers, we also have very detailed user behavior information associated with them. Information like, when's the first time, or when's the last time that I see this identifier being used? What is the number of fraudulent accounts I see associated with this identifier? What is the ratio of new users originating from this identifier? What are the common geolocations of these users that are associated with an identifier, and more like this. So we have this rich set of common digital identifiers and the user behaviors associated with them. And as I mentioned earlier, we have this production unsupervised machine learning system running that's been pumping out these labels for fraudulent accounts for the last 4 years. So we have data, we have a lot of features, and we have a lot of fraud labels, which is kind of rare. So the question becomes, hey, can we use a really smart algorithm like deep learning to discover these intrinsic relationships between these digital identifiers and the user behaviors? Can we generate some type of score? It can be a fraud score, or it can be a score indicating how good this user is, based on just these common data fields. And with that, let me hand it off to my coworker, Arthur, that will describe how we tackle this problem.
All right. Yeah, thanks, Team Fang, for the wonderful introduction. So these days, when people look at deep learning, it's obviously been very successful over the past few years. And these successes have been mainly observed in areas like computer vision, natural language processing, or other applications like AlphaGo, etc. So if you ask why deep learning has been so successful, one of the driving reasons behind it is the fact that deep learning models' performance scales as the amount of data goes up. And this is in contrast with traditional machine learning algorithm who doesn't have this nice scalability with amount of data, as shown in blue curve here. So along with the tremendous success, deep learning tools or frameworks have been evolved significantly in recent years as well. Shown here is just a suite of different deep learning frameworks that's out there and pretty popular among the users as well. But on the other hand, if you look around and see who's applying deep learning in production, a lot of the times, or majority of the times, you look at bigger companies like Google and Facebook, and rarely you see smaller startups applying deep learning. And I summarize the major difficulty behind this phenomenon into two aspects. And the first top reason is the fact that access to large amount of data, especially label data, is very limited. And fortunately for DataVisor, as Tim Fang mentioned, we have this we have a pile of data that's ready for this purpose. So we seem to be okay on that front. But another really big hurdle is actually the technical side. So it takes a lot more efforts than to build a production-ready deep learning system than just being able to train a deep learning model with a certain framework. So here is a really nice figure from Google, which just showcases the amount of efforts it takes to bring machine learning or deep learning models into production. So the size of the squares here in the figure actually is proportional to the lines of code it takes to develop certain modules. And if you look at the center, very tiny, small black box in the center of this figure, that's the amount of machine learning core code that resides in Google machine learning system. And just quote from this paper, the required surrounding infrastructure is vast and complex. So that makes the barrier of entry to deep learning for smaller startups really high. So then, let's take one step back and think, hey, this is Spark Summit, right? So why don't we take a look at, why Spark? We all know that Spark has been very successful. in terms of simplifying the workflows for the big data analytics for different users. And why has it been the case? To summarize, like really briefly, I think top 3 reasons pop in my head. And the first one is the fact that it's a unified engine, such that it's it's an end-to-end solution. So data engineer or data scientists who work with Spark doesn't have to mess up with different frameworks for loading the data, for performing MapReduce computations, for saving the data to different data stores, etc. And along with it comes with very simple API and also various optimizations under the hood, which really brings up the computation speed and reduce the computation time for users. And Spark also handles the distributed computing for the users, so such that data scientists who work within the Spark ecosystem doesn't have to know too much about the complicated distributed system behind the scene. So these are all really nice features. And if you really want to pick on Spark, I guess here's one thing: like deep learning integration is still under development. So as you have probably heard from various previous talks within even this summit. So on the other hand, TensorFlow, being one of the most popular and successful deep learning frameworks out there, has really nice benefits. Claimed by Google, it's production ready. It summarizes the many years of production experience by Google into this package, if you do it right? And then it also supports extensive machine learning APIs for various tasks, which allows users to perform deep customizations into even every single computation within your machine learning algorithm or deep neural network algorithm as well. So, but along with it, it comes with a couple of downsides. So the first one is if you look into what TensorFlow API provides you in terms of data preprocessing capabilities, most of the APIs are geared towards more well-studied deep learning fields like computer vision or natural language processing. So for our application in anti-fraud, it really doesn't have the amount of support that we need. And plus, as a company who has production mainly in Java, we have a lot of existing features or code that we would like to leverage in our deep learning pipeline as well. So, but if you look at TensorFlow, the best supported API is in Python. So obviously there's a mismatch in terms of language. And along the same line, TensorFlow is just not an end-to-end solution yet. If you think about the previous figure from the Google paper, that like what TensorFlow offers is really majority of the functionality within the little black box that provides the machine learning core capabilities, and the surrounding modules are on their way to be open source, but that's not happened yet, and that's out of scope of today's topic. Okay, so then how can we combine Spark and TensorFlow? And as you have heard from various previous talks, especially the last talk within this room, TensorFlow on Spark and developed by Yahoo, and also Databricks offerings like deep learning pipeline and TensorFrames, and all those are very interesting offerings to combine Spark with TensorFlow in order to kind of bring the benefits of both worlds into the same pipeline. But again, we look at these offerings, they are still geared towards like well-studied areas like computer vision or natural language processing. For us, we have our own special needs when we actually develop a new deep learning model for anti-fraud space. So to think through the problem, let's start with machine learning workflow. So really roughly speaking, you can separate machine learning in production into 2 phases. The first is training and then serving. So for training, you have some raw data, and then you derive certain features or perform feature engineering on the raw data. And then you pick your deep learning framework and pick your model architecture, and you train your model. And then you want to evaluate the model performance on certain test data set. So you probably also want to repeat the training and evaluation process multiple times until your model performance reaches a certain threshold. And then you say, hey, my model is ready for production. So I'm going to deploy in a production setting, in which case I'm going to serve the model to serving data. Let's call the data in production as serving data. And serving data can come either in batch or real time. And similarly, you also want to derive features on this data, and then you want to apply your models and generate inference results. So, okay, so a couple requirements in our case, like along with the typical machine learning workflow. So first one, we actually want to treat anti-fraud application. This is more a generic requirement. We want to treat the application as a classification problem, such that a user is either a good guy or a bad guy. And second, we want to maintain the training and serving consistency in terms of feature engineering, such that when you derive features, you don't want to maintain two sets of code, and hopefully they just share the same set of code, and that's just not nicer to maintain and productionize. And the third one is a little bit interesting in our case. So we want to support post-analysis in order to better understand model performance. Because if you think about what we're trying to do here, what we're trying to do here is apply deep learning to a new application, in which case we don't have existing state-of-the-art computer vision models or CNN models available, but instead we actually need to try different model architectures and try different features, try different combinations of features in order to generate the best models. So so I just want to elaborate on this front a little bit more. So imagine you train your models through TensorFlow, and you get your model, and you have some test data set that you want to see how my model performs on this data set. You get a serious score for every single entry of this test data set. So the first thing you're probably going to do is to generate certain machine learning metrics, like how's my RC curve going to look like, what's my F1 score, and what's my area and the curve, those kind of stuff. But again, like in fraud spaces, there are some complications, and I think these complications are probably also generalizable to other machine learning applications as well. The first one being the fact that, hey, the labels. So if you think about fraud, as Ting Fang mentioned, like fraud is kind of a general term. For example, like in massive registration case where fraudsters register, tens of thousands of accounts, and these accounts are just bad accounts. And as a service provider, you probably want to just block those accounts or delete those as your action. And in another case where the fraudster may just log into your account and perform certain fraudulent behaviors, and we call those account takeovers. And in those cases, you don't want to block these poor accounts, but instead you probably want to notify the user and say, hey, your account is compromised. You probably want to update your passcode, etc. So different source of labels can, if you mix those kind of two different fraud scenarios and just treat both of them as bad guys, and that probably doesn't make sense. And if you notice those kind of things happen in your training process, you probably want to take this insight and go back to your training phase and clean up your labels first. Another really important requirement that we want to support is actually being able to explain your results or your prediction or your model. And then you may be wondering, hey, like, Arthur, are you crazy? Like, you're talking about deep learning, like, most of the models are probably not really explainable. But in anti-fraud case, a lot of times, just being able to give a score saying this is a bad account is not enough. But a lot of times, it's actually required by law to provide a reason. So to kind of work around this problem, we actually want to understand, hey, what are the top contributing features of my model that triggers a certain prediction? And can we actually come up with heuristics or like experiences to explain, hey, these set of users are probably fraudulent, and that requires serious data science analysis on the results. And then it's slice and dice. So after you have your model trained, a lot of times you actually when you train your model, what if you have really imbalanced labels? Likely, within your data set, over 90% or 99% of the users are actually good users. So you don't just want to throw the imbalanced label training data into the model, and likely your model will perform really bad. So, and then you probably want to downsample on a good user and rebalance the labels. And then you may be wondering, hey, if we mess up with the model balance ratio, and how will my model perform in the real world like serving setting? And these takes serious data science efforts to understand the model performance, and also sometimes your model doesn't perform uniformly across the different subset of your data, and you probably also want debug on FN and IP as well. Okay, so with all those requirements, like I just want to say, hey, being able to post-analyze on the inferred data is actually crucial for model development. in our use case. Okay, so how do we solve some of the pain points that we just mentioned? So for pre-processing, we want to stay within Spark side. And notice here, we actually want to share the same feature engineering across training and serving stages. And then once the data pre-processed, we actually leverage TensorFlow for modeling and for providing inference APIs, etc. And then we want to come back, hopefully, to Spark, especially Spark SQL, to analyze on the inferred data. Okay, so I will mainly talk about the Spark sessions. So first, let's start by looking at the pre-processing steps. So for pre-processing, we actually try to leverage Spark SQL APIs and load data into data frame. And for deriving features, one of the patterns we really like about is to apply user-defined functions. So each user-defined functions can be treated as, it's built from a particular feature function. That function either applies certain logic to derive a feature, or it takes in one or multiple columns and maybe join with some static data and derive your feature. So that way, after operating this UDF on your data frame, a new column is going to be generated, and you do this repeatedly with a set of UDFs to derive your new features. And once that's done, you have your pre-processed data that's ready for modeling purpose. And then the feature functions can be used for serving phase, in which case, think about real-time serving when every single entry of data gets pumped into your system, you can actually apply the series of feature functions on every entry of data point, and then generate the feature vector, and then throw that feature vector through TensorFlow for inference results. So that way, we can share the same set of feature libraries, if you call those, across training and serving phases. To support post-analysis, we actually leverage Spark SQL, as I mentioned. So we start similarly with data frame APIs. Say you have millions of test data set that you are curious about, and you want to apply your newly trained model to this data set. And then you perform similar feature derivation, which is similar to the training phase, and you got all the features you want, and then you probably want to apply the model. So for applying models, we actually leverage TensorFlow serving for loading the models, which is trained by TensorFlow. And the TensorFlow serving is a standalone package provided by Google. That's pretty lightweight. What it does is it loads a pre-trained TensorFlow model into memory and set up a simple server that's ready for a client to call to send a request to it, and then it returns inference results. So remember, we want to stay within Spark SQL side. So we actually developed client. Especially in Java side, to talk to the TensorFlow model. So what the client does is it takes every entry of your data frame and serialize that and generate the feature vectors and serialize it and send it to the TensorFlow serving, and you get a predicting results. And then what we also do is we actually regenerate a new data frame with this new column called predictions. So that way you actually have one-to-one mapping of all the features you have from a particular data entry, and also the associated inference score. So if you think about this, so you started from a certain test data set, and then the end result is all the features that triggers certain prediction results. So what you can do then is to, hey, what happens if I drop certain features? So you just remove a certain UDF from this pipeline, and then feed the same data set into the model and get a different score. So that way it can facilitate you understand how different features actually contribute to certain detections. Okay, so some other tips. So here, map partitions and singleton patterns. So when we actually perform the batch inference, map partitions and singleton pattern really comes handy, because instead of sending every single row directly to the TensorFlow server, which is going to stress up both on the Spark side and also TensorFlow side, we actually take each partition and kind of batch them together and then send it to TensorFlow server. And that way you also don't need to reinitialize all the feature libraries that you probably want to exert on your test data. And then UDFs versus RDDs, we talk about how we like the fact that UDFs come handy in terms of deriving features, but UDFs is really nice for deriving features, or like one single feature from one or multiple incoming columns. So sometimes you want to have this multiple to multiple feature derivation, or one to many feature derivations. So that, if that's the case, maybe using RDD is another option. So it just simplifies the code and makes it easier to maintain. And Java Spark versus PySpark. So for large scale, multi-million or even hundreds of million testing or batch applications of the TensorFlow models, we actually leverage Java. It's just we have a lot of Java, existing Java production experiences, etc. And PySpark is really nice for development purposes. For example, you have a new idea, you want to apply a new set of feature into the data processing and see how that performs, how that helps with your model development, etc. So having both become pretty handy for this model development. And then I want to point out to this particular TensorFlow ecosystem in which there's a Spark TensorFlow connector, which comes handy for saving data frame into TensorFlow records, which is ready for TensorFlow to consume. So with all those information, I will hand over to my colleague Ting Fang, who's going to talk about some of the results that we have.
Right, thanks, Arthur. So we have this production deep learning system that takes as input raw data from our clients, extract these common fields from this data, adds these auto-derived features to it, and then outputs a score according to the model. So how well does this work? Well, the first thing we evaluated was whether this combined signal from the deep learning model was indeed better than an individual signal from a single common digital identifier. Now, IP blacklist, email domain blacklist, and user agent blacklist have long been used in the security community. So here we also use them for comparison. Now here, these blacklists are generated from the same data sets that we use to train the deep learning model, except the process is much simpler. We calculate the number of fraudulent accounts over all user accounts associated with this identifier, and then classify any one of them as bad if this number is over 0.95. And the user would be classified as bad if it uses one of these bad identifiers. Now you can see from this figure that these blacklists have pretty limited precision and recall, much worse than the combined signal from the deep learning model. We're also serving this deep learning model to select production clients. And so this figure shows the improvement of the deep learning model over previous production results. The x-axis is the detection gain over the previous model, and the y-axis is the precision of the deep learning model. And each data point on this graph corresponds to a different score threshold for the deep learning predictions, ranging from 0.1 to 0.95. And you can see that even in the most strict case, we can provide a 10% detection boost over the existing model at 92% precision. While we leverage all of our clients' data to train the deep learning model, we can also incorporate additional labels, additional examples from a specific client in order to boost the model performance for that particular client. And in this figure, it shows the difference in the number of detected fraudulent accounts, starting from the previous production model on the far left to the improved version with the generic deep learning model trained on all the clients, to the even better version on the far right, where the deep learning model is trained on an even more biased data set with more examples from the target client, though using the same data fields. So I think I'm running out of time here, so I'll quickly summarize. This talk would describe how combining Spark and TensorFlow can lower the adoption bar for deep learning applications, especially when you're a small company, you're on limited budget and resources, and you're trying to apply machine learning to a less well-studied domain. There's some lessons that we took away from this process. The first is that feature engineering is important. This is not surprising, but in the for security applications in particular, there's a lot of domain expertise and heuristics that you can get from human experts that are very valuable. There are also a lot of contextual information or semantic information in the data that may require some transformations or embedding so that they can be used effectively by the model. Just think about all the categorical features in our digital data. And we already emphasized on this, but it's really important to understand your results, analyze it, make sure you know what your model is doing. Like, what do you do when the model is not performing well? It will probably happen. Now, is it your label data? Is it your training data? Is it you just need more features? Is it something specific to your test data that's biasing your results? Maybe it works for a different client, just not this one. Maybe it works for this fraud case, but not for others. So it's really important to understand the extent, or I should say the limitations of the model, not just so that you can produce defendable results, but also you know where to improve. And lastly, we're very proud to have successfully deployed this deep learning model in production and observed consistent improvements over the existing models. And with that, I think we can thank you and take questions.
So we are actually right at the time for this section. So if you have questions for our speakers, could you please take those either at the back?